So we're going to look at logistic regression's cost function now. Recall from our previous post lecture is that cost functions can be engineered from two criteria. We might choose to create a cost function based on plausibility. We know certain hypotheses are worse than others, so we're going to try to engineer a cost function that's going to be able to rate bad settings of theta worse than or have a higher cost than fairly good settings of theta. If we don't have a plausible hypothesis, we can actually just try to find something that's mathematically convenient for us to optimize. And the great thing about logistic regression's cost function is it satisfies both of these criteria. It's both plausible and quite friendly to optimize. So we're going to look at this idea. So for each of the points, x, y, we're going to say that it's going to be generated, the label y is going to be generated by an actual ground truth target function, which we can't see. This is the function f. And we're going to generate this plausible cost function based on likelihood. What we mean by likelihood here is what we've seen before. It's the idea that we have some data and we want to know, given the data, what are the best model parameters that's going to help me generate a good hypothesis. Okay, so how do we do that? We're going to just assume for a second that we magically found the right parameters, theta. So we have a hypothesis that accurately replicates the target function f, which we can't see. Then we want to ask ourselves, how likely is it that we would obtain the output y from the input of x? And this is pretty easy to write out because we have the notation for exactly what this means. If I have an input x, the possibility of it being a positive case in logistic regression is just the output. It is the probability of the positive class as defined by the sigmoid function, right? And if I have a negative class, so y equals -1, then it's just going to be 1 minus that property. Okay, so that's exactly how likely, because we're measuring the genuine probability of the output y. So let's continue. What we're going to do is just copy down what we had from the last slide. Okay, so we have the formula for the likelihoods. We're just trying to maximize the likelihood of the probability of generating the entire data, meaning both the x and the y's jointly. So the first thing we're going to do is we have these two cases, the positive case over here and the negative case over here. And we're going to substitute in what we mean by the hypothesis, right? So we're going to expand that out. We know that we're going to take the sigmoid function and we're going to put what in through the sigmoid? We're going to put the signal, which is just the weights transposed times the input that we see. Okay, and we know what the sigmoid function looks like. It has this form that we see on the right hand side of this diagram here. And when we want to try to generate a maximum, there's this problem that we have these two separate cases. So we don't want to do that. We want to analytically have an easy time of putting both of these cases together in one way. So what we're going to do is similar to what we did in the week 3 post, where we're going to collapse both of these cases into a single case. So how do we do that? We're going to notice that we can actually get both halves of the sigmoid from a single half. It's a mirror reflection. If we look at this point here, let's call that point x. Then the value of x is just simply 1 minus this value here, right? So the 1 minus the positive x value will get you the value of negative x on the other side. So we are going to take note of this property, and you can see where we're getting here. What we want to do is just use the fact that we have a -1 for the negative instances and use that as a multiplier against the sigmoid function itself to generate this. So when we are able to do that, we can collapse both of the cases into one. It's probably very trivial for you to see that this holds in the case of a positive classification, but for a negative classification, I'm going to get a minus sign here, right? It's a minus 1. I'm going to multiply it against my signal, and that's going to be able to calculate the same thing as 1 minus g of s, right? The sigmoid of s, because of the properties that we just looked at. So that's really nice. What we want to do next is just continue with that and say that the data set, which is the joint observations of the inputs as well as their labels, are just samples that are IID, meaning they're independent and identically distributed variables, and that allows us to write them out as a product. That means for all 1 to m training examples that I have both a label and observation seen, I can write it out as this conditional probability. And when I expand it out using this term here, I'm going to just get this, right? I have the sigmoid function, and then for every particular instance's label and its observation, I'm trying to maximize this likelihood, right? And so what am I maximizing against? I'm just maximizing against whatever choice of weights are going to make this product a large number, right? Bigger than any other setting. So we're just going to bring the same term over. This is the thing that we're maximizing over all of the individual instances, 1 through m, that I've gotten to see. And I'm choosing the set of parameters that's best going to maximize this value. So what things can I do to make this more into what we already know about cost functions? Well, cost functions are minimized because we don't like cost. It only happens when we have misclassification. So what we want to do is get this maximization of the likelihood into a form that's equivalent to what we do for cost functions. So how do we do that? We're going to do it step by step here. Well, first we're going to ask ourselves, could we take this and rewrite it something like this? Right, where I'm just taking the inner part of this, okay, and then taking a natural logarithm. Well, I can do that, right? Because when I do that, I have a positive value over here. The sigmoid function is generating positive values because of the way we flip the cases. The natural logarithm is monotonically increasing. It'll have the same maximum point as the previous equation here. So that's okay. What we also want to do is say whether we want to scale it. Maybe we want to scale it by 1 over m, where m is the number of examples. Is that okay? Yeah, well, that's just dividing through a constant, so that's fine too. And you can see what's going on here. We're trying to get it to the same form of what we're doing for minimizing. So the next thing, minimizing a cost function, right? So we can flip the max into a min. That's easy. We're just going to minimize this value, right? Just the negative of that. From 1 to the mth example of all of the things that we have here, our sigmoid function, right? Times yj transpose of the weights that we get to tune. Okay, and what are we going to do next? Well, we can push in the logarithm. So we're going to get the product to come out. It's going to turn us into a summation. And this is starting to look really good because we have it in the same type of formulation as we have seen before, right? Which is to say that we have this part over here, which is basically looking at aggregating all of the individual costs and putting it together, cost function over the entire data set. So we're just looking now over here, what can we do about that? So we're going to copy that nicely for you, and this is what we have. Using some algebraic manipulation, we can just do some of that by pushing in the negative sign all the way through, and then we'll get a minimum of 1 over m, same summation of going through all m examples. But now the logarithm, the negative sign has flipped what we had in the middle here into a reciprocal, right? So we have the sigmoid function and the same yj times the transpose of the weight vector times the individual observations j. Okay, so that's looking pretty good. We're going to expand that out a little bit more. We're going to write down what this g function, the sigmoid function, is, and that's easy because we can just plug it in. We're going to plug in this value for g of s as 1 over 1 plus the exponent of the signal. So we can write that out. So we have two reciprocals. They're going to cancel each other out, and we're going to end up with this form here, right? So that's really good. We have now the formulation of the cost function. Again, if you look at this part here, this is actually our point-wise cost function, because we're going to later aggregate it over the entire set of examples and the average of them and minimize the average, right? And so we can think about that exactly as the point-wise cost function that we have here. And this is basically, when we take it through all of this, is the average cost of any individual, of all of the individual points. That is our cross entropy error. And that finishes our derivation. So in logistic regression, we're minimizing this particular pointwise cost. In linear regression, we're minimizing this one over here, right? And the intuition is pretty much the same, right? When there's a big difference in the scores that are predicted by the signal and the actual output class, we have a large distance, and then we're going to square it in linear regression. For logistic regression, and again, we're going to look at just this part over here, right? So when, let's say it's a very large number, when we multiply it against another positive, let's say +1, then because of the negative sign, we're going to get a very small amount. So then basically it's a wash, right? Then on the other side, if we have a negative example and we believe highly that it's a negative example, so it's the signal itself is very negative, then again we are going to get a positive value for this part, and it'll be negated. So what happens? We get pretty much nothing from this term. This term will go away. Of course, you can see how it works for disagreements. If we strongly believe that this is a positive case, but yet it's actually negative, then we have this term as being a negative. And when we have the negative sign in front, they'll turn it into a positive. So it will be a really, really large term. And that will cause a big jump in the cost. Flipping that, let's say we have example that we strongly believe that's negative, but actually it's a positive case. The same thing holds. We'll get out a negative term here, and because of the front negation, that'll turn another chance into a very positive value, and we're still going to end up with a big penalty.